Alright, let's discuss higher order models with a temperature control lab. Here we have this model we've discussed where we have our heaters, but we also have a model for our sensor as well as our heater temperatures. And we look at how that works. We've discussed state space models before. Here we have our three differential equations. We will change heater 1 and see how that affects heater 2 and heater 1, as well as the temperatures for sensor 1 and sensor 2. So we'll go ahead, we're going to work on a state space form similar to what we did before. So we'll have QC1, QR12, and then this tau where we have some of the lump parameters. And so the first thing we want to do is we want to run a step test and then regress our parameters. So we'll go ahead, similar to what we've done before, we'll either try to read matrix, and if that doesn't work, we'll go ahead and loop through manipulating Q1 and leaving Q2 constant. We'll then go ahead and write it to a matrix and save it as a CSV, and then turn off our temperature control lab. Then here's the part that's part of the assignment. The first step is to regress our parameters as we've done before. Here we have U, the heat transfer coefficient, US, which is the heat transfer coefficient for convection and conduction between the two heaters. Then we have alpha 1 and alpha 2, and then tau, that lump parameter. Again, we're using fmin here, which is constrained minimization of our objective function. Because the inequality constraints are of the form ax is less than b, for our lower bounds, we'll do a -1, and then what the lower bound is, and negative as well. And then for the upper bound, we'll just do 1 is less than or equal to what the upper bound is. So go ahead, we'll run this first snippet, and we'll see how we're doing. So our initial objective function is evaluated at 4.6. Similar to what we've done before, our objective function simulates these physical models. Let's see what this error is. Local minimum possible. So it's possible that we reached a local minimum. Let's see what are our parameters. U is 1, US is 10. Alpha 1 and alpha 2 seem realistic. Actually, they seem opposite a little bit, to be honest. And let's see. Tau is equal to 32. That seems realistic. Let's go ahead and let's look at, we should graph our fit. There we go. The real problem is that we're starting at a lower temperature than we'd otherwise assumed. So let's go ahead and let's go to our objective function real quick, and let's just see if we can set that. P45. T0 is equal to T and naught. Here's our model. It's differential temperature, then we sim the model with ones. What's that initial T0? It's equal to sim. What if we set all of those equal instead of these simulated values? Our T is, okay, so our sim model takes the argument T naught. And where does the sim model get the T naught from? So it takes time, sim model, which is this right here, takes arguments time, Q1, Q2, and then params. And then from params, where do we get Q1? Oh, it's the first argument in sim model. Let's see. Okay, so sim model, where's our objective function? So we give it our first times. And our simulated one Alright, so C is the difference between the two squared. That makes sense. Okay, so let's just say instead of the first measured one, let's just set it to the second one. Maybe that first one was a bad value. Unless we've done this process before of using an objective function that minimizes some squared error and regress our constants. By now, this process should be rather familiar. See, we're already a little bit lower. That's a good sign. And we're doing better. You know, I can live with that. We should be starting down here. I think that's due to some bit where we plot. Yeah, we plot right here as well. Let's do this really quick. Instead of T1 starting at 23, what we're going to do is we're going to say we'll connect to the lab earlier. So we'll just cut this line. And we'll put it right here then. And instead of 23, we'll do lab.T1. We'll actually measure the temperature. So that's what we'll do with our data. Because I already have my CSV saved, what I'll do is I'll just take the second point for this sim model. And that will be our initial condition. We'll run it one last time. Just want to see a pretty graph. Our next step, though, is going to be to regress the state space model coefficients. So we'll do that. We've done something similar before. There we go. That looks pretty good. Look, you can hardly see the blue line. That's a good looking graph. All right, let's move on now. So now we're going to simulate the state space model. We're going to get the transfer function of temperature to sensor as a response to heater 1 changes. So you can see right here, there's our transfer function right here. We have how we change TC2, the state of TC2, with respect to all of these other variables. So we have these different equations here that are differential equations at a certain heat and at a certain temperature. For example, the change in F1, which F1 is going to be the change within our heater 1 derivative with respect to Q and T is going to be this relation right here. We've done this before as well, except this time rather than having simplifying values, I went ahead and we're just going to plug them in. So I went ahead and plugged some of them in beforehand just to save some time. So here are some of our constants. And I noticed there's one thing missing, so we'll get to that there. Here we just pull everything off to the right hand side, and remember, because these are our deviation variables, our T prime, we're going to have the ambient temperature or the initial temperature raised to the third is what's left after the derivative. So we have U times A, we have the radiation, we have the heat transfer between the two, and the radiation between the two heaters, and then all of that divided by mass times Cp. Then as far as how heater 1 affects heater 2, we have just the transfer between the two divided by mass times Cp. Then for heater 2, these are the same coefficients as heater 1, just reflected. So it's how heater 1 affects heater 2 is going to be what's in A21, and how heater 2 affects itself is going to be the same as A11. Then we have 1 over tau, and negative 1 over tau. Remember, those coefficients are from right here. And if we look at our state space form up here, we can see what that's modeling is how the heater affects itself, and how heater 2 and sensor 2 affect one another. And that's obviously going to be opposite. Any heat transferred from one will go to the other. The last bit is how heater 1 affects the Q1 affects heater 1, which is going to be alpha 1 divided by mass times CP. So we'll go ahead now, run this section again. I didn't have that divided by mass CP. We're going to create our matrices now. And now we have our state space model. The last thing we'll want to do then is we'll want to actually use our state space model. So I've gone ahead and I've added the steady the signal space that would allow us to do a state space model. That's what this sys-ss is. We'll go ahead, we'll create our steady state system with our matrices. We'll go ahead and give it some initial conditions. And then with this LSIM, we'll simulate our system with the inputs U and time T. Finally, we will go ahead and plot it. And we would plot the state space equations with as well as the measured data. The one problem is that as we've seen before, I actually don't have the I guess those brackets are unnecessary. I don't have the package to run this. We need the control toolbox, and because I have a limited license of MATLAB, I'm not able to do this. But I'd be happy to help you if you have any problems after running this. Hopefully the code makes sense. Hopefully the rationale behind creating our system makes sense as well. We create our physical models, and we already have the constants that we don't know regressed. And so we're able to create this state space form and then model with it using state space functions. Thank you. Let me know if you have any questions.